Okay, in this class I am going to talk about the hybridization in square pyramidal molecules. Hybridization in square pyramidal molecules. I have given the geometry of the square pyramidal molecule here. You can see that this is a central atom, and connected to the central atom there are 5 groups or 5 atoms. And 4 of these atoms are in the corners of a square base, and another atom or group will be in the top of the square. Okay. So this is a square pyramidal structure, and we are going to assign what is the possible hybridization in this type of molecules by means of group theory. And we have done this for several types of geometrical structures. In our previous class we will be adopting the same method here as well. Okay, and it is very easy as well. And in order to understand how the hybridization works in this case, or how the hybridization evolved in this case, we have to first understand the symmetry elements present in this type of a geometry. So first of all, we have the C4 axis, and the C4 axis is this axis itself, right? The axis, for example, let me say these vectors as R1. For example, I will take the vectors through the bonds. Okay, so these are the bond vectors. This is R1, and this is another bond vector, that is R2. This is another bond vector R3, and this is R4, and this is R5. Okay, so let me call these bond vectors by these names. And the C4 axis is the axis which is passing through R5. Okay, so this is the C4 axis. The axis passing through the R5 vector is the C4 axis. And then we have C2 axis as well. What is the C2 axis here actually? Actually, what is written as C2 axis in this character table is the C4 axis itself. When we are carrying out the C4 2 times, that is equal to C2. Okay, no other C2 axis you can find here. So you have a identity E, then you have C4. C4 can be done as C4 2 times, or we can write C4 square and C4 3 times. Okay, out of this, C4 2 times is equivalent to C2. So instead of writing C4 2 times, you can write it as a unique element C2, and it forms a separate class also. That is very important. And in addition to that, so say for C4 and C2 are the same axis. Okay, in the case of C4 axis you are rotating 90 degree, but in the case of C2 axis 180 degree rotation is there. And then you can consider two sigma v planes. Sigma v planes are the vertical planes, that is, the planes containing the principal axis or C4 axis. So this vertical plane will be perpendicular to the plane of the square base, and it contains the principal axis as well. So one of the planes will be through here, means it will contain R1 and R3 and R5. Okay, a plane containing R1, R3 and R5. Another plane containing R4, R2 and R5. Okay, here is that plane. So these, you remember that these planes are actually perpendicular to the plane of the square base. So two vertical planes you can see like this, and each of the vertical planes will contain 3 bonds. In this vertical plane sigma v, you have R1, R3 along with R5, and in the other sigma v plane you have R2, R4 and R5. Okay, so 2 sigma v's are there, that is why it is written here in the character table as 2 sigma v. And in addition to that, you have 2 more vertical planes. They are actually dihedral planes. Okay, and these planes will also be perpendicular to the plane of the square base, but this plane will be bisecting the angle between any bonds. Okay, so for example, you can consider a plane like this, a plane passing through this line. Okay, and this plane actually bisects the angle between R1 and R2, and at the same time it is bisecting the angle between R3 and R4. So that is a sigma d plane, and this plane carries the R5 also, or the principal axis also. Okay, so sigma d plane contains one of these bond vectors. And you can consider another sigma d plane. That sigma d plane actually will be bisecting the angle between R3 and R2. So it will be bisecting the angle between R1 and R4 as well. So this is also another sigma d plane. This sigma d plane is also perpendicular to the plane of the square base, so it will carry the R5 vector also. So now you know all the symmetry elements present in this point group, and this molecule therefore belong to C4V point group. Okay. And now we are going to construct the total character. The total character is constructed based on the number of vectors retaining their position during each operation. So total character in this case I am going to construct. So gamma t or total character is, in the case of E, how many vectors are retaining the position? There are 5 vectors from R1 to R5. All the vectors are retaining the position during identity operation, because identity operation is equivalent to doing nothing. Therefore, all the vectors will retain their position, and therefore total character corresponding to E is equal to 5. And what about C4? C4 is the rotation about the R5 in this case, right? R5 vector. Therefore, only R5 vector will retain its position during the C4 rotation. All other vectors will change their positions. Therefore, the character corresponding to C4 is equal to 1. Okay. And what about C2? C2 is considered as the same axis as the C4. C4 അതേ ആക്സിസ് തന്നെയാണ് C2. അപ്പോൾ C2 ആക്സിസിലൂടെയും C2 ആക്സിസിൽ ഉൾക്കൊള്ളുന്ന വെക്ടർ എന്ന് പറയുന്നത് R5 തന്നെയാണ്. Therefore, only one vector will lie in the C2 axis. Therefore, that vector alone will retain this position. All other vectors will change their position. Therefore, the character corresponding to C2 is also equal to 1. And what about sigma v? Sigma v, the vertical planes. The vertical planes actually contain, each of these vertical planes, sigma v planes, contains 3 bonds. In the first sigma v, you have R1, R3 and R5. Like that, in the second sigma v, you have R2, R4 and R5. So 3 bonds will be there in each sigma v plane, and those bonds or those vectors which will retain their position will be contributing to the total character. Therefore, the total character corresponding to sigma v is equal to 3. And what about sigma d? You can see that in the case of sigma d, only one vector is present in the sigma d plane, that is the R5 vector in this case. Therefore, the total character corresponding to sigma d is equal to 1. So, the total character set is 5, 1, 1, 3, 1. Now, the next task is to apply the reduction formula. Right? Because you know that corresponding to this total character set, there is a reducible representation. And you have to find out which are the irreducible representations in the character table contributing to this reducible representation corresponding to this total character set. That we can find out by reduction formula. And the reduction formula is Ni is equal to 1 divided by H into sigma, then GR chi IR chi R. This is the reduction formula. Ni is equal to 1 by H into sigma GR chi IR chi R. You already know the definition of the terms here. GR is the number of classes in an irreducible representation corresponding to an operation. For example, if you are considering the operation C4, GR is equal to 2. If you are considering sigma V, GR is equal to 2. If you are considering C2, GR is equal to 1. So, chi IR is the character corresponding to any operation R in the ith irreducible representation. For example, if you are considering the first irreducible representation A1, corresponding to C1, the character is 1. But if you are taking B2 as the character set or B2 as the irreducible representation, corresponding to C4, the character is -1. Now you know chi R. Now you know chi IR also. Chi R is the character corresponding to the operation R in the total character set. So if you are taking C4 as the operation, the corresponding character is equal to 1, that is appearing in the total character set. And Ni is the number of times the ith representation will appear when we are reducing a reducible representation corresponding to this total character. And now we can apply the reduction formula and find out the number of times each reducible representations will appear. So we will be using only those irreducible representations corresponding to some atomic orbital. We can see that A1 is an atomic orbital corresponding to some atomic orbital, because Here we have dz square, and obviously s orbital is there, then pz orbital is also there. Then we can consider B1. We don't need to consider A2 because there is no atomic orbital corresponding to A2 in the character table. Now we can consider B1 because corresponding to we have dx square minus y square orbital. And then we have to consider B2 because corresponding to B2 we have dxy orbital. Then we have to consider E because corresponding to E we have px, py, then dxz and dyz orbitals. Okay, so in that except A2, we have to do the calculation for all other irreducible representations. So first of all, let us find out NA1. So NA1 is equal to 1 divided by H. What is H in this case? That is the total number of non-redundant operations. What are the total number of non-redundant operations in this group? 1 plus 2, that is 3, 3 plus 1, 4, 4 plus 2, 6, 6 plus 2 is equal to 8. So H is equal to 8 in this case. Order is equal to 8. Okay. So we have to calculate NA1 now by giving H 8 in place of H. So 1 by 8 into sigma gr chi r chi r. So we have to do this for every r and then sum it up, right? First of all, let us take the first one. All the characters here are 1. Okay, so it is very easy to calculate this one. So gr in the case of E is equal to 1, then 1 into 1 into 5, that is equal to 5, plus 2 into 1 into 1, that is equal to 2, plus 2 into 1 into 1, that is equal to 2, plus 2 into 1 into 3, that is equal to 6, plus 2 into 1 into 1, that is equal to 2, that is equal to 5 plus 2, 7, 9, then 15 plus this is 5 plus 2 plus, okay, 1 is missing here. What is missing here? 5 plus 2 plus 5 plus 2 plus 1. Okay, here 1 is there. Corresponding to C2, there is a 1. Okay, this is 1, not 2. 1 plus 6 plus 2. Okay, so that is equal to 7 plus 8. So 8 plus 2, 10, 16. 16 by 8. 16 by 8, that is equal to 2. So NA1 is equal to 2. Okay, NA1 is equal to 2. And what about NB1? NB1 is equal to 1 divided by 8 into, now you can apply the same procedure for B1. Okay, here we have 1 minus 1, 1, 1 minus 1. So if you are applying this characters, then that you can write it like, okay, that is 5, okay, then minus 2, then 1 plus 1 plus 6 plus into minus, okay, then minus 2, okay, that is equal to 5 minus 2 plus 1 plus 6 minus 2, okay, then 5, 6, 6, 6, 12, 12 minus 4, that is equal to 8, that is equal to 8 by 8, that is equal to 1, okay, and NB2 in this case is equal to 1 divided by 8 into 5 minus 2, the character set is already here, okay, B2, 5 minus 2 plus 1, then minus 6, then plus 2, okay, so 5 plus 1, 6, 6 plus 2, 8, 8 minus 6 minus 2, that is 0, so 0 by 8, that is equal to 0, okay, and NE is equal to 1 divided by 8 into, then we have the character set here corresponding to E, so we will get a 10, then plus 0, minus 2, then plus 0, plus 0, okay, that is 10 minus 2, 8, 8 by 8, 8 by 8 is equal to 1, okay. So we have the results like 2a1 plus b1 plus e. Okay, so total character set corresponds to chi t corresponds to 2a1 plus b1 plus e. Now we can calculate now we can take the sum of the dimensions in order to check whether this result is correct or not. Okay, so if we are taking the dimensions, a1 is a one-dimensional representation, b1 is also one-dimensional representation, e is a two-dimensional representation. So this is one-dimensional, this is one-dimensional, this is two-dimensional representation. So if you are calculating this sum of the dimensions, 2 into 1 plus 1 into 1 plus 1 into 2, that is equal to 2 plus 1 plus 2, that is equal to 5. And this 5 should be equal to the number of hybrid orbitals that you are expecting. You are working with a square pyramidal complex, so you have 5 vectors there. So that is correct. You have 5 here, so that corresponds to the 5 hybrid orbitals. Okay, so you have to always check this in order to see whether your calculation is correct or not. And now you have this result, chi t is equal to 2a1 plus b1 plus e. So let me write it here. 2a1 means the hybrid orbitals will be composed of 2 of the a1 sets, or 2 atomic orbitals corresponding to the a1 symmetry, and then it will be combined with one atomic orbital corresponding to the b1 symmetry, and then it will be combined with the atomic orbitals corresponding to the e symmetry. And here you have to note that this is the two-dimensional set, therefore you will see the doubly degenerate sets in this one. Okay, so 2 orbitals will be actually contributed by this e set always. Okay, so let us check the a1, b1 and e sets. So looking at the character table, you can see that corresponding to a1 you have 3 orbitals. What are the 3 orbitals? Is dz square is there, and then pz is there. Then in addition to that, s orbital is there. S orbital is totally symmetric. Even if it is not written in the character table, you have to consider that. So s, pz and dz square, these are the orbitals there. S, pz and dz square. Okay, so our result says that any of these 2 orbitals will be utilized for hybridization. So we have 3 pairs. Either it can be s and pz, or pz and dz square, or s and dz square. So any of these 3 pairs will be utilized for the hybridization according to our results. Okay, and what is the atomic orbital corresponding to b1? Corresponding to b1, you have dx square minus y square, right? There is only one orbital corresponding to b1, therefore that is a compulsory orbital, dx square minus y square, dx square minus y square. And what about e? From e you will get the degenerate set, doubly degenerate sets, right? What are these doubly degenerate sets available from b? That is px py is a doubly degenerate set, and dxz dyz, these are also doubly degenerate set. So we have to have that also. So px py, okay, these together, and dxz dyz, okay, these together. So we can have either of this one because it is 1e. So 1e will be equivalent to px and py together, or dxz and dyz together. Okay, so there are actually 6 combinations possible. Okay, 6 combinations possible. What are the 6 combinations possible? We know that dx square minus y square is always compulsory. So this one can be combined with either px py or dxz yz. But there are 3 pairs from this one, because we can take 2 orbitals of a1 symmetry. Either it can be s pz like this, or it can be pz dz square like this, or it can be s then dz square like this. So either of these pairs will be combining with this one. Okay, so these will combine with dx square minus y square, and then it can combine with either of these pairs. So how many possibilities are there? And then there are 6 possibilities, right? 6 possibilities. So let me write the possibilities of dx square minus y square px py set. Okay, first set this one. and how these sets will combine with these three sets. Then we will get three possibilities. Then I will consider ds square minus y square combined with these d orbitals, the second set, and how the second set combines with these three sets. And then that will give three more possibilities. So totally there will be six possibilities, right? So the possibilities are S plus P Z, S plus P Z, that is this set, okay, X plus P Z, plus dx square minus y square plus px plus py. This is one set, okay. Next set possible is Pz dz square, Pz plus dz square plus dx square minus y square plus px plus py. Okay, that is the third set. And the second set. The third set is s plus dz square, okay, plus dx square minus y square plus px plus py. Okay, these are the three possibilities from there, and the other possibilities are there. This s plus pz plus dx square minus y square plus, now we will be using dz orbitals, okay, d orbitals, dxz plus dyz, okay. And then we have pz plus dz square, pz plus dz square plus dx square minus y square plus dxz plus dyz. And then we have the last possibility s plus dz square plus dx square minus y square plus dxz plus dyz. So these are the six possibilities by symmetry, okay. So symmetry allows all these six possibilities, no problem by symmetry. But the final hybridization, the choice of hybridization depends upon other factors as well. Symmetry is one of the factors, okay. And in addition to that, there are other factors like energy, orbital availability, etc. And based on this, a suitable hybridization will be selected in each compound, okay. For example, if you are considering the first one, this is 1 s orbital plus 3 p orbital plus 1 d orbital. So this can be dsp3 hybridization, right? dsp3 hybridization, or it can be sp3 dehybridization also. In the difference here is that in the dsp3 hybridization, d orbital comes from the inner shell. Here the d orbital comes from the outer shell. That's the difference, okay. But by symmetry doesn't say which orbital, whether it is inner shell orbital or outer shell orbital. That is not said by the group theory. Group theory only says that what are the orbitals possible to combine by symmetry, okay, or how the symmetry allows the orbitals to combine. The other factors should be determined by the quantum mechanical results and also from the consideration of the orbitals available in the atom itself, okay. So if you are taking one of the examples, a common example is pentacyanonickelate 2 anion, okay, pentacyanonickelate 2 anion, that is NiCN 5 times 3 minus, okay. So in this case, the nickel atom is in the plus 2 oxidation state. Nickel atom is in the plus 2 oxidation state, Ni2. So it is pentacyanonickelate 2 anion, Ni2. So the electronic configuration of the nickel in the zero oxidation state is, nickel's atomic number is 28. Therefore, it is 3d8 4s2. Okay, 3d8 4s2 4p0. Okay, this is the electronic configuration when it is a neutral atom. But when it is nickel 2, means Ni2 plus, then it will be 3d8 4s0 4p0. Okay, so if I am representing this by the boxes, these are the 3d orbitals, 5 3d orbitals. Then this is the 4s orbital, and here is the 4p orbital. Okay, and you have 8 electrons, right? 8 electrons. So 1, 2, 3, 4, 5, 6, 7 and 8, it should be like this. But when it is forming the complex, this will be paired. Okay, so it will be paired like this. Then you have one vacant d orbital, and this vacant d orbital, then it will combine with the 4s and 3p orbitals to give dsp3 hybridization. dsp3 hybridization like this. Okay, so this is a dsp3 hybridization. dsp3 hybridization. But you have to note that the d orbital utilized here is dx square minus y square. That is very important. ds square minus y square. Okay, the d orbital utilized here is ds square minus y square. So this one is dx square minus y square, and this is a s orbital, 4s orbital, and this is px, py, and this is a pz orbital. Okay, so dx square minus y square, yes, px, py and pz, these are allowed to be combined according to symmetry, right? Yes, pz, px, py, then dx square minus y square. So these are allowed to be combined by symmetry, and these orbitals are combining, then you will get a square pyramidal arrangement. And here you have to note that in the last class or in the previous class, we were learning the trigonal bipyramidal case. Trigonal bipyramidal case. There also the coordination number is 5. So here also the coordination number is 5. Square pyramidal also is the case of coordination number 5. So in the last class, when we were dealing with the trigonal bipyramidal case, okay, trigonal bipyramidal case, there also we saw the dsp3 hybridization. dsp3 hybridization there also, the trigonal bipyramidal case, right? So in the trigonal bipyramidal case, there also you saw the dsp3 hybridization. But what were the the orbitals in that case? You have to remember that this was like a dz square. Okay, dz square. Then s orbital. Then px, py plus pz. This was the case in the trigonal bipyramidal case. Okay, here you have to note that here we have two orbitals in the z direction. dz square and then pz orbital. Both of these have the orientation in the z direction, right? And there we saw the structure of the molecule. There we had three atoms in the xy plane, okay, or three bonds in the xy plane. This is the xy plane, three bonds in the xy plane, and two bonds were perpendicular to this xy plane. Means this is in the plus z and minus z direction, right? So two bonds were in the z directions, and corresponding to these two bonds, there were two hybrid orbitals. And these two hybrid orbitals were obtained because there were two atomic orbitals in the z direction, dz square minus y square and pz. These are the two atomic orbitals in the z direction, and because of this combination, you got two hybrid orbitals in the z direction. Okay, that is a case of trigonal bipyramidal geometry. Okay, even if you will see the same type of hybridization, the d orbital involved there is different in order to get two orbitals in the z direction. But here in the square pyramidal case, the case that we are considering now, there the d orbital is dx square minus y square, and there is only one orbital having z orientation. What is that? The pz orbital. Okay, therefore when these orbitals are combined, you will get only one hybrid orbital in the z direction. So that is the case with the square pyramidal case, right? Square pyramidal. So this is xy plane. So four orbitals will be in the xy plane itself, and one orbital will be in the z direction. So that is why you get one atom combined from the z direction, and other four atoms combined in the from the xy plane itself. So this one, this one, this one, this one. These four will be combined from the xy plane, and only one will be combined from the z axis, because there is only one z orbital involved in the hybridization. So you get only one hybrid orbital in the z direction. So even if both are d sp3 hybridization, there is a clear difference. In the case of square pyramidal, dx square minus y square is used, which is having the occupation in the xy plane. But in the case of the trigonal bipyramidal, dz square orbital was used, which has the orientation in the z direction. So this difference you should note. So the group theory tells us clearly which are the orbitals involved in different types of the hybridization in different types of geometries. Okay, and I hope you understood this one. And if you have any doubt, please don't hesitate to ask me. And this is the last geometry that you have to consider by group theory according to our syllabus. So we have considered almost 5 geometries so far, right? And we considered the geometry, the coordination number 3 means trigonal planar. Then we considered the coordination number 4, two cases of coordination number 4. One is tetrahedral and another one is square planar. Then we considered the coordination number 5, two cases. One is trigonal bipyramidal and other one is square pyramidal. Okay, so we have completed all the geometries mentioned in our syllabus, and I hope you understood this much. I hope it is easy for you and you can write well in the examination as well. If you have any doubt, please don't hesitate to ask me. Thanks for watching and stay tuned.